Hello, and welcome to Lecture 24 of AMAT502 at UAlbany. Today, we're going to conclude our content for this semester. We're going to take a look at the future and what the future of data science holds for us. I'm going to try to end the lecture with a description of some of the theoretical challenges that underlie data science, but most of this lecture is meant to be practical. In particular, I'm going to give you some details on what your final projects and presentations should look like. Additionally, we'll revisit the question of what is data science and try to take a larger view, which is going to essentially take us to this perspective of what is the underlying sort of financial motivation behind data science. I'm going to try to highlight the importance of good communication and visualization and point towards the things that we haven't been able to address in this class, but which you should pursue on your own. And then conclude with this final question of what is there more to do from a theoretical standpoint in data science? So these details may change, but I want to just give you at least a sense of what I'm looking for when we look at these final projects and presentations. So again, we have a in-person presentation component, or at least virtually, and then a written presentation, a written project afterwards. So as a reminder, each individual on the team gets their own individual grade in the proposal and also in the presentation. So I should say presentation, which makes up 40% of this final grade. I think the number now is closer to 30%. Presentations are 10 to 20 minutes long, and every person on your team needs to be prepared to speak from at least 2 to 5 minutes. As an individual, I'm grading you on essentially the following 20-point rubric, which is a question of preparedness. How well did you explain your method and why you used it? Is it clear that you rehearsed your portion of the presentation? Visualization is going to be really important. How nice are your plots? Did you title appropriately? Can you explain your visualizations clearly? Again, this is all for the presentation. Analysis. So I want to show that you thought about it. What did you conclude based on your data science methods? When we did our analysis using a Bayesian classifier, where we're trying to decision trees where we use entropy as the criterion for splitting, we were able to reverse engineer some of the results and get an idea of, what are the meaningful attributes to classify on first. So how good was your method? What was your accuracy? What inferences did you draw related to the problem in hand? That's just like what I discussed. What are some further directions for research if you had more time? I understand that we only have a limited amount of time to pursue research in this class, but something's better than nothing. And you could ideally indicate where you'd like to go. So remember, we need at least a 4-page single-space LaTeX, and I emphasize it needs to be in LaTeX. Final report due 2 weeks after the presentation. Paper is graded for the entire team, so everyone gets the same 60% of their final grade. And again, this 25% number, I think is now 30. Check the syllabus for the semester. All right, so the final project, Writeup. So in addition to the presentation, there's the Writeup. And this is something which is graded as a team. So every individual in the team will get the same grade for this portion of their final presentation and project grade. The rubric looks something like this. So again, I make it out of 30 points just for easiness. Use of LaTeX, it's 2 points possible. Did you hit your minimum page limit? Maybe I'll allow 4 pages for some, but you should really be shooting in the 5 to 10 page range. Again, 2 points possible. How good is your introduction and your abstract? 5 points. Explanation of the why. Why should I care about this? 2 points. Visualization. So here, there's a greater premium on making sure you have nice typeset graphics. So there's 5 points there. You should be able to explain your results clearly. And then also assess the quality of your models and results. So these two have some overlap, but I want to go ahead and provide. There's a difference between interpretation versus just assessing accuracy. So I think of this results explanation as maybe more of the inferential step. What were the greater conclusions? And then being able to talk about how good was your model Did you play around with the parameters, so on and so forth? Future directions, what you'd like to do if you had more time, and then also a job distribution statement. So here's some general advice, which should hold for a lot of different things, but please check for grammar and spelling. We do have some opportunities for having someone review your final reports at UAlbany. You can ask me more about those details later. It's not necessary, but please be mindful of your grammar and spelling. Motivate the problem and describe your methods and findings in lay terms. I want you to pretend I'm a manager who's educated, but maybe doesn't know the specifics of data science. Additionally, try to interpret your findings and tell a story. Again, explain why you chose those methods and how good of a job. That goes into those 10 points in the final write-up. As an example, in Project K-means, even though I specify that you should use K equals 5 and K equals 13 because we're trying to map onto letter grades and letter grades with decorations, you could have also played around and be like, well, actually, some of our best clustering comes from looking at K equals 4. Above and everything, you need to make sure you're ethical. So please be honest. If you have no findings, report that, but also make sure that you tried lots of different things. Again, if all your results are negative, then you should show that you did try lots of different methods. We have, unfortunately, this culture in science that negative results aren't worth publishing about, but maybe you're saving someone time by reporting on negative findings. All right. Make sure you're a good collaborator. Use clear communication amongst your team so everybody knows who's doing what, and let's make sure there's consensus. Working in groups can be very difficult, but it's an important skill to develop, and unfortunately it only gets better with practice. And I just emphasize here, in your final report, you need to explain at the end who contributed what to the final project. Some scientific disciplines like biology actually require more spelling out. In math, we tend to be a little more opaque, and that's why we use alphabetical ordering. We assume everyone worked equally. The other thing is, please, please, please do not fake your data. I don't think that's going to be much of an issue based on the proposals I've seen so far. But I would just want to tell you about a really important example that I learned about when I was a postdoc at Duke. So there was a researcher, doctor named Anil Pati, who essentially faked data in order to get published in some of the most attractive scientific journals, Science, Nature, and things like this. And then this also got him an upgraded job. He got a fancy job at Duke. He also was able to pull down large amounts of money, grants, and he even set up chemotherapy trials based on his sort of fraudulent findings. And once this was all come to light, because another team, I think in Texas, tried to replicate his findings, they found that they couldn't do it. And then they noticed small lies on his CV, such as talking about a Rhodes Scholar that wasn't actually a Rhodes. And eventually the patients and people sued Duke for millions of dollars, and Duke had to pay back the American Cancer Society over nearly $730,000. Research ethics is, again, something we could devote a whole lecture on, but again, be genuine scientists. And there's more I would like to say on this in another class or iteration on this. All right, so let's step back. So now you have some sense of rules of thumb for the final project and presentation, but I want to kind of step back and have a broader view of what we've been doing in this class. In the first lecture, I introduced Drew Conway's Venn diagram for data science. And we thought of, data science as being sort of an intersection of math and statistics knowledge. We've definitely been doing more probability and Bayesian analysis than I have in previous iterations of this course. And again, something I'd like to flesh out in more detail. We also just try to develop your hacking skills. Can you handle some of the basic concepts of computer science, write little functions that do what you need to do, but then also interact with the Python ecosystem. hey, why isn't pip install working? Have you tried using conda install? All this just goes underneath hacking skills. And hopefully you've developed some hacking skills during the course of this semester. And then finally, there's that subject matter expertise. So each of you is picking some project, perhaps it's related to sports, perhaps it's related to medicine. We're gonna need to learn something about the actual subject you're studying. And that's what makes actually being a data scientist exciting, is you have the opportunity to integrate your hacking and math skills and learn something new. I would say my main critique of this diagram is not necessarily, doesn't necessarily describe data science as a set of ideas, but rather as a set of skills. So let's consider, again, a more philosophical interpretation. And what is the science in data science? We really want to try to understand what the end goal or purpose of data science is. Joel Gruss, whose book, Data Science from Scratch, I've used a little bit of, says, a data scientist is one who turns data into insight. So you need to be able to draw some broader inferences, think critically about what your methods are telling you. I'd argue that when he says insight, it's sort of being self-referential. It's just a vague synonym for science. And indeed, if you think about the root definition or meaning of the term science, science comes from this PIE, that's the Proto-Indo-European root, supposedly the Ur language of a lot of languages. Ski, which means to cut. So science is all about incision, insight. And I'd say that, one of the things that a scientist does is it tries to, comprehend the world. There is a really good comparison or allegory in one of Plato's dialogues, Phaedrus, where he talks about, things that a scientist needs to do is comprehend scattered particulars with one idea. So how do you take a bunch of disparate observations and then generalize into some grander hypothesis? But another part of that is dividing species according to natural formation. And this is where a very famous phrase gets used in Plato, where he says, you want to divide where the joint is, not breaking any part as a bad carver might. So this whole idea, you want to, cut at the joints of the universe. So basically, science is all about the attempt to know, to cut away from untruth, find truth, and to make sure that that truth is sort of carving the universe at its joints. So that's a really nice idea. And I would say that actually that broader idea of like a scientist is trying to carve the universe at its joints is really one of the reasons why I'm passionate about understanding the interaction between unsupervised learning and supervised learning. But there's also a really practical side of data science. And this is that data science has become a method for value extraction. Harvard Business Review called data science the sexiest job of the 21st century. And there are plenty of people doing really good knowledge extraction who aren't being rewarded. So I would say that, unfortunately, from a businessman's point of view or business person's point of view, what makes data science sexy is not its value extraction. It's not its knowledge acquisition. It's value extraction. And here I have something like, I think this is $1 billion or something, all packaged up and photographed on pallets. Indeed, like data science is making a lot of people a lot of money. And in fact, this idea is prevalent at other data science programs as well. So Hal Varian, who's chief economist at Google. So again, Google is essentially like its own nation state. And he's also a UC Berkeley professor where they have a really great data science program. He said that the ability to take data, to be able to understand it, to process it, to extract value from it, to visualize it, to communicate it, that's going to be a hugely important skill in the next decades. So again, we're now understanding that data science isn't purely about knowledge acquisition. It's extracting insight, it's visualizing, it's communication, and also processing. So some of you might want to know more about data mining, for example. And that's something you're going to need to pick up somewhere else until we like fill that gap in our curriculum here. But I'm going to point out a lot of the ways in which we are doing a good job here at Albany. So let me go ahead and counterbalance the sort of more high-minded scientific aspects of data science with the more sort of economic aspects. So let me give you some examples. So there's this nice article that goes through all the ways in which data science has been able to lead to value extraction. Southwest Airlines has saved over 100 million US dollars by just using data science to characterize and reduce the amount of time its planes stand idle on the tarmac, waiting for takeoff. I mean, planes are not fuel efficient vehicles. And so anytime that it's spent powered up, waiting for delays and things like that, it's literally burning money. You aggregate that over lots of planes, that's a lot of money. Additionally, UPS used data science to save something like 39 millions of gallons of gas. So then multiply that by the number of dollars per gallon, because it was able to figure out how to optimize how it routed its deliveries. The IRS has been able to recapture something like $2 billion in tax revenue by basically writing programs that are good at automatically detecting whether or not people are either doing something fraudulent or maybe they didn't add up numbers right. So again, just interfacing with computation, you have a chance to make a lot of money. So this is why I like this other Venn diagram. And so essentially, data science isn't just this Venn diagram of math and statistics, hacking, and subject matter expertise. But rather, it's a diagram where a lot of different skills come to play. So the data scientist Venn diagram that others have drawn includes it's an intersection of business and programming and statistics and communication. And I kind of like how there's this deeper breakdown of what are the different positions that focus more on one rather than the other. If you're not doing any programming, stats, or communication, then you're probably maybe just an accountant. Maybe if you have a little bit of statistics, you're doing more number crunching and analysis. If you're actually then communicating those results. The salesperson sort of lies inside of communication and business, but doesn't have any of these other skills. The data science consultant, that sort of sits right here in the intersection of these four sets of skills. That's really what you want to be. You want to be a good business person. You want to be a good programmer. You want to be a good statistician. You want to be a good communicator. I know it's a tall order, but again, people are very highly compensated for their skills if they're able to balance out all four of these. And I'll say that this all leads you to the question of, well, how do I get a data science job? So part of the problem is that the term data science is a little vague, and it can run a huge spectrum from being a machine learning expert, someone who has a PhD in machine learning, to a software engineer who happens to like math. And this is sort of expressed when you use websites like levels.fyi, which is meant to help people coordinate offers and things like this. So I think it's interesting if you add in, let's say, Netflix here, you can just get an idea of what's the compensation for different level engineers. Right now, this is underneath software engineer. But I'll just point out that I've heard that a senior software engineer at Netflix, apparently everyone has this sort of level because you can see they only have that category, can make almost $4.5 million in salary and then some stock, or $450,000 a year in salary and some extra compensation and stock options. Maybe if you're looking at Google level 3, that's 187,000. Again, some of that is being compensated by stock options and then bonuses and things like that. Level 4, even more, so on and so forth. So you can kind of sit around and play around and fantasize a little bit about, and here if we go at, data science, they've got some median figures here, and you can see some figures here, Amazon, Oscar Health. So the bottom line is you're not going to get a job at one of these big tech companies right out of a data science master's. You really need to hustle and build some experience. And in particular, there's a lot of outside work from just like sitting in on these classes and doing your homework. You need to really take this upon yourself to transform yourself into the kind of employee or even startup entrepreneur that you want to be. There are lots of books that help you prepare for coding interviews, because all these jobs have several rounds of competition. You need to be prepared to succeed at every one of those steps. I copied this 2-page flow chart out of Cracking the Coding Interview. It gives you sort of an idea, but I'd recommend you pick up the book because it's one of those things that might be really handy and at least provide you some essentially like interview prep, like you would do a test prep for a standardized test to get into this program. And again, this project, it starts long out. So over 1 year before your interviews, you need to be doing outside coding. You need to learn multiple programming languages. You need to be networking. You need using sites like LinkedIn to help build your network. You need to have a nice website and portfolio, which showcases your expertise and your experience. As most of your students, you need to be trying to land that first internship, and that can already be competitive. And then take classes with large projects. We had a couple large projects in this class, and I'm hoping we can expand these offerings soon. For professionals working on these sort of meaty projects is good. And then we have this whole sort of 3 to 12 months, in game. Again, building more projects, draft resumes, sending it out, getting people's comments, make a target list of preferred companies, reading these intro sections, and then getting into some of the more computer science focused things. Like make sure you have things like, big O notation down, how to implement data structures and algorithms from scratch. That's one of the reasons why I suggested Joel Gruse's Data Science from Scratch book. Get together with your friends and do mock interview panels. Keep doing these sort of mini concepts and practicing sort of interview questions. And then you just essentially begin repeating and continuing. But, one of the things that I want to emphasize is that some of you might be really fabulous coders, but you need to work on, say, your communication skills. Or maybe some of you are very natural communicators, but you need to really help refine and polish your coding skills. The one thing I want to really emphasize is that good communication is so valuable. It's sort of hard to tell the difference between a great coder and like a very good coder. But if you can tell the difference between a great communicator and even just a good communicator, that ends up probably paying off or making a bigger difference. To that end, the question of how do you communicate well? Communication occurs in all sorts of different forms. But I'll point out that 70% of the human brain is built for visualizing things or dealing with visual input, which is one of the reasons why, don't just deal with like the standard options on your figures. Really try to become a matplotlib or Seaborn wizard and make really compelling graphics. And this leads me to, someone who's become sort of a cult hero is Edward Tufte. And so Edward Tufte is a really interesting character. So he was a Yale statistician and artist. And he became sort of famous for writing this sequence of books called Visual Displays of Quantitative Knowledge. I'll share more of that soon. But one of the things that Tufte helped popularize was this graphic depiction of Napoleon's failed invasion of Russia, where he called it one of the best statistical drawings ever made. And essentially what's happening here is it's a really beautiful sort of multimodal graphic. We have these like the width here indicating how many soldiers, we have the color indicating, what was the marching out, and then black indicating the return march. And as people essentially split off and die, this this band becomes thinner and thinner. So you have a sense of the trickle of soldiers who are coming back. He also has this sort of amazing correspondence with the temperature and other things like elevation. So it was and this is an old graphic from, I think probably the late 1800s or something, but essentially characterizing this march from 1812 to 1813 in Russia. Some more information on Tufte is he was hired by Princeton to work at the Woodrow Wilson School, which is essentially the school of public policy. He taught courses on political economy and data analysis, and actually had to self-publish some of these books later. But while he was pushing these quantitatively inclined political science books, he had this remarkable opportunity happen where in 1975, Tufte was asked to teach a statistics course to a group of journalists. Again, in our current crisis of sort of COVID-19, understanding statistics and being able to report on it accurately in the media is such an important skill. And so being able to transfer that knowledge was a really great service of Tufte, even though it was in sort of, less dark times. One of the things he did is he developed a set of readings and lectures on statistical graphics. And he took this to form a joint seminar with an extremely famous statistician by the name of John Tukey. Anyone who knows something about Tukey. And so all of this led to essentially his first book on information design, which was this visual display of quantitative information. It kind of looks like this, and now it's in its second edition. So one thing you might consider if you can afford it, and this is to your liking, you might consider taking a one-day course with Tufte. So he goes around and makes money essentially running seminars. If you're a student, you can get all 4 of these books, Visual Display of Quantitative Information, which was his first one, Beautiful Evidence, Envisioning Information, Visual Explanations, like all 4 of these for $240. And that includes the price of the one-day course. I have not personally done it, so I can't attest to how good it is, but you should be aware of it. There are a few other books on graphic design, Stephen Few, Show Me the Numbers. And all this is just going to creating clean looking plots, which are visually appealing and which help communicate complex information in clean, straightforward ways. So I kind of want to swing back. So I was trying to sort of speculate more broadly on what is science and how is data science a science, even though it doesn't fall into this normal sort of causal prediction paradigm that characterized physics, for example, for hundreds of years. And then even though I went into like, well, really it's about making money. And one of the ways you make money is you have to be a really good communicator and make good graphics and, how to deliver a good elevator pitch and master all the steps for a coding interview. Seems like a lot, but let's sort of step back again and try to think about the intrinsic interest in this subject. So data science is not entirely about making people money. I'd say in maybe its highest form, it's just about uncovering patterns in data. And that's really something that every experimental scientist must do. I'd argue that even scientists who don't think of themselves as data scientists probably have to use some sort of regression. So, what's the trend? They have to do some sort of classification. When is it like this and not like that? When are 2 things similar and 2 things different? It's clustering. And how can I understand my data in a easy to visualize way, which often comes from dimensionality reduction. So I'd argue every scientist maybe use these skills, but doesn't necessarily know the algorithms and methods that we've learned in this class. And I'd say that experimental scientists give us knowledge about the world, which is inherently a good thing, but better data science techniques would then sort of feed back and allow these scientists to do their jobs better and squeeze more information out of data. So in this sense, I really think of data science as a blend of science and engineering, because you also are trying to optimize something. You're tinkering with something. It's not so, passive and empirical. Often a data science method can emerge directed towards perhaps maybe an uninspiring engineering application. So if we think back to some of our early classification lectures, we're like, we ask the question, does this image have a picture of a cat or a dog or not? So that's a simple image classification problem, which might seem, sort of silly in the grand scheme of things. But if you think of that, you realize, well, that's just trying to take an image and classify something in there. What else could I classify? Well, for example, you might be doing something a little more noble, like suppose I have a MRI scan of a tumor and I want to classify, is it cancerous or benign, malignant or benign? So I would say that even though culturally what separates a scientist from an engineer is the degree to which one focuses on empirical questions, such as what is the case? Engineers tend to be focused on imperative questions. How do I accomplish this task? And in this sense, actually, data science answers a really inextricably linked question, which is, how do I know what is the case? So that's really, again, a question of epistemology. How do I know things? And so this then sort of leads you to the question, well, how can I engineer my methods to then better know? So in that sense, again, it's a blend of science and engineering. So in our example above with the tumor classification, we need to learn something empirical, and that is hopefully going to be reflected in the algorithm. So at some point, and this is one of the reasons why I try to dissuade a little bit from neural nets, is that because it's black box, like ideally we'd like to be able to reach inside the black box and figure out what is it that the machine is doing that decides a tumor's cancerous or not. And how can we turn that into human understanding? So this sets me up for then a question and a lecture, which we decided to omit this semester because I didn't really feel like I could do it, justice, given already all the material we've done. But I do want you to be aware of there is an opportunity to just play around with your own sort of neural net. And you can do things like try to classify what are orange points and what are blue points. And then you can essentially use this sort of graph that feeds forward this. And you can see how very quickly the neural net was able to define a decision boundary where essentially it says on one side are blue points and on one side are orange points. One of the things you end up seeing is data which has this sort of interesting spiral shape can be very, very difficult for a neural net to essentially identify or separate. And that's because often the math which goes into carving out these decision boundaries have some what I'll call topological limits. So I'll just sort of pause that and return. Feel free to play around with the TensorFlow. And even though we learned how to eventually separate radial data by using sort of a kernel trick and radial basis functions, there are things like this spiral network where you really have a lot harder time. And you could try some combinations of different functions to get at it, but it'll take a while to carve those decision boundaries out in a way that accurately separates the blue spiral points from the orange spiral points. Again, notice that this is, for us as humans being able to look at this figure, it's very easy for us to separate out what are blue points and what are orange points. But the whole theme of machine learning is we're trying to teach a computer to automatically do that for us. And this is going to be necessary in situations where we can't look. Again, data tends to be high dimensional. And so when we can't look, we need to have belief that our machines can identify patterns that we could, if we could see in those dimensions. So I'm trying to leave you now with sort of an appetizer or something to whet your appetite on how do we deal with these sorts of non-linearities, so these sort of spiraling data sets. And I'll mention that this is still an active and ongoing area of research. And this just goes to this notion of data that has latent structure. It's, hidden underlying structure, which is hard to simplify, but nevertheless, we believe there should be some simplification. Again, those spirals, they're not that complicated, but it's hard to teach a computer that. So one example of this sort of nonlinear data set that is is very famous, is something called the Swiss roll data set. And I'll point out that an algorithm which was able to identify and simplify the structure in the Swiss roll data set, something called Isomap. And this was published, this technique, Isomap, around 2000 by a neuroscientist, Josh Tenenbaum, who was at Stanford and then was at MIT, my alma mater, along with Venn, who is one of the great figures in topological data analysis. And I sort of lucky to have him as an unofficial mentor. And also John Langford. This paper here is where this technique for Isomap is described, and just to show you how impressive this development was. This has been cited over 12,000 times. I'm sure if I were to check again, it'd be up even more. And it's possible that it's even been cited more than Watson and Crick's 1953 article on the helix structure of DNA, which over a course of 60 years has been cited only 13,000 times. So just as a simple comparison, you're looking at citations per year, Isomap is vastly outperforming Watson and Crick. Now, of course, there are some important caveats to mention here. First of all, engineering computer scientists, they publish a lot more papers. They tend to be shorter. They tend to cite a lot more, just a lot more activity than say in more empirical sciences or even in math. In math, it's more common to write just a few papers that are longer, and mathematicians don't publish as much because they're sort of more interested in doing something more structural and fundamental rather than sort of just showing what the latest best performance is. Additionally, Watson and Crick's discovery has now become common knowledge, and people tend to sometimes stop citing things when it becomes common knowledge. Anyhow, Isomap is an impressive intellectual contribution, and I can describe roughly how this thing works, but I want you to know that there are other nonlinear dimensionality reduction techniques. So this kind of goes underneath the unsupervised learning dimensionality reduction, specifically in the nonlinear setting. So there's something called LLE, local linear embedding, multidimensional scaling, MDS. MDS tends to have fantastic performance in separating out classes of data. I'd also recommend TSNE, which is T stochastic neighborhoods embedding. Additionally, Laplacian eigenmaps. These are all things you should tinker around with if you're really interested in cleanly separating out nonlinear data into classes. But just to give you a sense of why we need these sorts of nonlinear techniques, one of the few dimensionality reduction techniques we went through in this class was principal component analysis, PCA. And that's because, essentially it treats the embedding and then just looks for variation in various directions and then just projects onto the direction with the greatest variation. So, because this is slightly oblong, it would probably project onto, the axis that my cursor is following, and then maybe also onto here. But that would totally just collapse out any of this sort of Swiss roll aspect. The points would just get laid on top of each other. You want to be able to see this structure. So here we're in this great sort of toy example where we can see in 3 dimensions that there is this structure, but we're trying to figure out how would we identify that structure, especially in situations that are higher dimensional. I'll mention that Josh Tenenbaum was also sort of a philosopher of sorts, where he was really thinking carefully about how do we perceive, how do we know things. And I tried to make this course of that flavor. Of course, one of the basic ideas behind this this article where Isomap was published is this idea that you can essentially fix a radius or a scale parameter and then build a graph, and then force yourself to measure distance along this graph, so that you then see that these points are actually not this far apart, the distance traced by my cursor, but rather they're this far apart, which is a proxy for the sort of Swiss roll or rolled up data set. And then being able to find these sorts of these paths and eventually then roll out our data set by doing these sorts of local structure identification by sort of just attaching nearby points with edges. But then of course it gets to the question of, what's the right scale? If I let my scale be as long as this dashed blue line, then I would start connecting those up and I would teleport. But how do I figure out what the right scale is? And this is just a little code to show that this data set is so well known. It's built into scikit-learn. You can just literally make Swiss roll and do sort of Isomap on it. Not something we're going to cover today, but you should be aware of it. So I mentioned this challenge of how do we pick scales? And essentially one of the nice things that Isomap does is it does do this thing where it sort of identifies a scale, and then it uses that to try to infer what's I'll call the true shape of our data set. But one of the immediate problems with that is we can't say for certain what scale is the true scale. So one method which we didn't get to go into, but I encourage you to use in your final projects if you find it useful, is this notion of single linkage clustering, which essentially studies how points connect at various scales. So obviously if your scale was 0, meaning you can really discern these points as being distinct and belonging in different classes, then you would just get, the total 7 points here. But if you imagine you sort of blur your eyes a little bit, then you'd see that, oh, well, points 2 and 3 are going to connect. And maybe if I blur more, let's see, what would be the next merge event? Maybe 1 and 7. Yeah, and indeed, you can read this off from this dendrogram, this tree, this upside down tree, where you see 2 and 3 merge at the scale 0.1, and then 1 and 7 merge into a single component at scale 0.25, and then 4 and 5. Yeah, they look like they'll be the next ones to merge at almost 0.4 scale. And then finally, if we keep going, then we start seeing that 2 and 3, which was a cluster, might merge with 6. And you end up getting this sort of family tree of when you enlarge your notion of relatedness, how do these clusters come together? So this is a notion of sort of parameterized clustering, where you don't fix the number of clusters ahead of time, but rather you just see, well, for what, range of parameters do we have a certain number of clusters? So again, it's sort of hard to say what the true answer is here, but we might say that, 2 and 3 belong in a cluster, and maybe 1 and 7, in which case maybe we're operating in this regime. Or maybe we're operating in this regime where there's sort of just 3 broad clusters consisting of, 6, 2, and 3, 4 and 5, and then 1 and 7 separately. So this gets to an area which is essentially my specialty and my expertise. And this is known as topological data analysis, which you can think of at the sort of simplest level as a new approach to clustering. Single linkage clustering in particular ends up being a sort of special case of a construction that is prominent in TDA. And so if you're interested in learning a little bit more about TDA, there's a really nice YouTube video by Matthew Wright, who was a classmate of mine. But I can essentially tell you a little bit about it. So instead of working with this sort of tree structure, you end up working with these, it's called the barcode. The barcode you can turn into a scatter plot of points by taking the birth time as the x coordinate, and then this upper endpoint, which is called the death time, as the y component. And so then this barcode would turn into something that has 3 points in the xy plane, or birth-death plane. But essentially what happens here is, if you've got some functional data, so you think of this as maybe like an intensity function on an image, so these points are maybe more intense than these, and so on and so forth. You imagine sweeping, so you look at sub-level sets. So you look at all the points in your image which have intensity below a certain threshold, but then you also realize that those partition into components. just has to deal with the fact that, whenever you have a generic smooth function on the real line, it's if you pick any level and you look at anything below that, it's going to decompose into a collection of intervals. And these intervals are the things that tell you the components. And so this is read off by what's called the merge tree, which is very much like the dendrogram and single linkage clustering, where, here I've got one component, here I've got another component, here I have another component. But then as I move up past this local minimum, or maximum, I should say, these two components are going to merge. And so then we lose a branch. Now there's this really nice fact that given one of these trees, you can always read off a collection of intervals, which essentially comes from looking at branch paths. And then whenever two threaten to merge, you let the oldest, the one that was born earlier in the filtration, continue, and then you let the youngest die. It's something called the elder rule. And so here, what this allows you to do is it allows you to featureize functional data like this, which can be really hard to store computationally, into a barcode, or equivalently this persistence diagram. So this bar here with the arrow pointing is supposed to go off to infinity, so we just sort of forget about it, and we focus on these more subtle points, which really correspond to the fact that we have these two local maxima here. So each local maximum caps off a bar. And so now what we have is sort of more topological representation of this function. And then we have ways of turning this into, points in a Hilbert space where we can apply things like SVM and other things like that. And this is sort of a nice way of featureizing. And again, I'm trying to get you to think in your final projects, like, what are my features here? Are they sort of high dimensional? Are they sort of interacting in complicated ways? But there's also this sort of nice fact that you could sometimes use these sort of topological representations of things like images to help compress, but then also simplify. So for example, if we have this, and again, it's topology, sort of the logos or the study of situation, of place, whereas topography, graphy, is drawing, or it's the representation of space. So here we're trying to study the essence of space. And so here, one situation where we get to both look at topography and topology, we can look at this sort of river basin map and see these mountain peaks. And essentially you have this notion of altitude. And you can see, because the terrain is very complicated, there are all these sorts of like small details. And indeed, if you were to take that sort of filtration of the function image that I gave you, but now study it for this two-dimensional image, and you see how these rings merge together, you would get also a persistence diagram, which kind of looks like this. But you could say that, well, I'm really interested in the fact that there are, 2 or 3 main points, which corresponds to these peaks here. So there's a peak here, there's a peak here, there's a peak here. And so one of the beautiful things about persistent homology, and it's one of the reasons it was invented, was, well, what I want to do is actually algorithmically compress and simplify my height function. So essentially, by identifying these 3 peaks, and you can identify them formally by looking at, what has the sort of longest lifetime in my persistence diagram. That's these 3 bars or 3 points here. There is actually in 2 dimensions an algorithmic way of getting rid of all the sort of noise, the little deviations in the land, and returning a new map, a new function, which only has those 3 points. And so that would just essentially help you do what's called mode detection in this image. So this is just meant to be an advertisement for what you might learn in one of our topological data analysis classes. And so I just try to impress upon you that topology of data is a really interesting thing. Not only does it allow us to compress information, and so in that sense, you can kind of think of it as a dimensionality reduction technique. It's really an expansion of the notion of clustering. And so dimensionality reduction and clustering were our 2 main branches sitting underneath unsupervised learning techniques. But I'd rather you think of, those are just two important branches of topology, clustering and dimensionality reduction. And so one of the things that I'll just try to advertise is that, topology is really seductive because it allows us to think sort of more abstractly about shapes. Like, what is it that's really truly different or the same about, this sort of angel statue versus this mother holding child statue? In a sense, all right, they both, the sort of angel touching her chin creates a loop between her index finger and chin and her arm, just as the sort of mother holding child creates a loop here. And then we've also got her resting her arm on her knee, and then that creates another loop, which you might identify here, and maybe her feet are touching, and that's what can be identified with this third loop here. Or imagine we look at, Leonardo's David. To what extent can we imagine David as just this, what's called two-holed torus, T-O-R-U-S. And these sorts of beautiful graphics were developed in this paper, an efficient data retrieval parallel read graph algorithm. You can think here, again, the legs with the feet kind of corresponds to a hole. And again, this sort of arm touching itself might be another hole, but maybe this is different because then the arm touching down here is another sort of feature. And so topology is the thing that kind of allows you to stretch and imagine these things the same. And you're lucky to be at UAlbany. We have a long program in our data science master's program, which helps teach you the foundations of statistics, which again, as we already saw, is one of the really important branches in data science. We also have, unlike most universities in the world, we have a program dedicated to topological data analysis. And this comes from the several faculty, including myself, who specialize in TDA. So if you're interested in sort of that direction, I encourage you to take some of these courses. And then we have a long sequence in machine learning, although this one sort of it touches on a lot of those methods as well, where we've got our sort of function theory and functional analysis, optimization methods, and nonlinear programming, and then a machine learning 592, and then a practicum. So we've kind of already done a little bit of both, but here you have the opportunity to go deeper. If you're interested in learning more about TDA and you want to see how maybe this fits into the broader framework of either marketability inside of your future career, or maybe you're just interested in learning more and want to maybe do a little side research, you can come and speak to me or email me after class. All right, but I want to conclude with this sort of this catchphrase, which I'll attribute to Gunnar Carlson, one of the key figures in TDA, which is that topology is the ultimate nonlinear data analysis toolkit. So with that, I thank you for your attention and efforts this semester, and I look forward to seeing you in class soon. Bye.